In this lesson, we're going to be looking at Objective 3.2, Properties of Solids. So this objective states, explain the relationship among the macroscopic properties of a substance, the particulate level structure of the substance, and those interaction between the particles. So first things first, when it comes to the properties of liquids and solids, they're going to be determined by two things: the strength of the intermolecular force as well as the type. Because if we know the different types, that can help us figure out strength. But remember that strength can also be changed based off different factors like charge, size, more electrons. Those are things that we have to also keep into consideration. I'm going to just put that in there as well. So here, thinking about charge, size, and electrons for strength, because that can affect it. Between intermolecular interactions are broken when a substance vaporizes. This thing called vapor pressure and boiling point are directly related to the strength of those interactions. So first things first, boiling point. This is the temperature at which a liquid converts to a gas. Okay, this is just a phase change. Now, vapor pressure is going to be a new word that we probably haven't heard before, but here, this is the pressure exerted by a gas, and we say this gas is in equilibrium. We haven't gotten to our equilibrium unit yet, but all that means is that the gas and the liquid are going to be in this back and forth relationship in a closed system, a closed container. I'm going to put closed container. So here the pressure exerted by a gas to convert a liquid to a gas. So you can see in the diagram to the right that these molecules are pressing down on the liquid. So this right here would be my gas, this would be my liquid. And yeah, the gas molecules are pressing down, forcing that liquid to become a gas with it, okay? I do want to note a high VP, vapor pressure, means the gas is forcing the liquid more quickly to become a gas. So here, it's actually going to have a lower BP, boiling point. So here, what is that relationship between vapor pressure and boiling point? It's actually going to be inverse. So a high vapor pressure, low boiling point, or a low vapor pressure means a high boiling point. So interesting enough, there are some factors that can affect vapor pressure. The first one, let's talk about concentration. We haven't talked about concentration too much just yet, but concentration, if we have more particles, so more concentration means more particles, which is actually going to affect the vapor pressure and make it, there'll be a direct relationship for that. Next, intermolecular forces. Remember, IMFs help us understand strength, okay? So here, if we have stronger IMFs, we're going to have higher boiling points, which that's going to affect vapor pressure. It'll be a lower vapor pressure. And then lastly, temperature. This is going to go with that diagram to the right. Here, if we increase the temp, we're increasing the KE. This means kinetic energy of our particles. Our particles are moving a lot faster. So here, we will reach the boiling point much quicker. Okay, because yeah, if we're increasing the temperature, particles are moving a lot faster, and we know if our particles are moving a lot faster, we're getting closer to that boiling point. So yeah, if you look at this picture, you can see this would be our cold temperature. This would be our hot temperature, just looking at the increase of temperature. Here I only have like 7 molecules in the gas phase, but while we increase that temperature, we're getting more and more particles converting to a gas, okay? I know I'm just talking about boiling point, and technically this objective is on properties of solids. I want us to note that melting point can also correlate the same with all of this, because you have melting point first and then you have boiling point. They tend to be correlated, okay? But not completely, because energy is going to be completely different when we get in thermodynamics. So let's talk about the particulate level representations of solids, liquids, and gases. And I'm sure we have done this in a chemistry class before taking AP. So closeness of particles. Solids very close together, while our liquids will just be close together, not very close together like a solid. And then our gases will be far apart. When it comes to the arrangement of the particles, solids will have a regular pattern because they're going to be right next to each other. Liquids, they're going to have actually a they're going to be just randomly arranged because they're not necessarily going to be in a pattern, okay? As well as gases, they're going to be randomly arranged as well. Next, movement of particles. When it comes to solids, they're actually just going to vibrate right next to each other. So they vibrate in a fixed position. So even though we see solids all around us, and it doesn't look like they're vibrating, but on a macroscopic scale, they actually are moving back and forth, just right next to each other. Liquids, they're going to be moving around each other. But then our gases, they are moving around each other, but they're moving quickly in all directions. So I would say they're moving just around each other more quickly. Next, the energy of particles. This is going to correlate to thermodynamics, but we're going to talk about this later on within the class. Solids are going to have our lowest energy, while liquids, we can say greater energy or medium energy. Just for the sake of going low, medium, high, I'm going to put medium. And then gases are going to have high energy. And again, this can correlate with a lot of things. It's when we have solids right next to each other and we're just trying to break up a solid to a liquid, that's going to require a lot less energy than trying to break liquids to gases, okay? Just to draw a 2D diagram of what this would look like on a particle scale, the solids are right next to each other. They're a regular pattern. You'll see I drew them at the very bottom of that box. AP is going to be looking for things like this. A liquid, they're still relatively close together. I'm trying to show like a randomly arranged pattern. And then but I showed it at the very bottom of the box. And then when it comes to the gases, I'm going to show them taking up the entire box, okay? Because we don't know where gases are going to go, okay? All right, moving on. So since this unit is types of solids, we got to talk about the 4 different types. But one thing I want to note, when we think about a solid, you need to think melting point, okay? Let me put this right here, melting point. This is one thing we need to think about because questions are going to ask you where they give you a chemical formula and they'll tell you melting point or something. And you have to think about the types of solids. They're going to be looking for, did you classify the correct type of solid? Molecular, ionic, metallic, covalent network, okay? This is increasing in strength left to right, weakest to strongest. And again, this is a general trend, okay? We probably have not heard about covalent networks, so that's probably going to be our most confusing one. Types of elements presence. For molecular, we're going to have molecules, and these, or we can say, or atoms. And these are non-metals only. Here, ionic will be a metal, positive, and non-metal, which is negative. Then metallic, we have metals only. We can say atoms of electropositive elements, because our metals are going to have that positive charge, okay? Covalent network, we're going to say non-metals. Generally, when it comes to these, you might see carbon, you might see Si. There are other examples, but these tend to be them. You might see O sometimes, okay? And it kind of just depends, and you're going to see this is going to be probably the most confusing, but this part right here, melting point, is going to be our key factor in deciphering between our weakest and our strongest, because right now, molecular and covalent seem relatively the same. Their biggest difference is melting point. Type of bonding. These are going to be neutral molecules held by IMFs. All right, so that's LDFs, dipoles, hydrogen bonding. When it comes to ionic, we have ionic bonds, okay, electrostatic attractions. Metallic, we have metallic bonds. That's that metal with the sea of electrons. And again, this type of bonding is indicating intermolecular force, okay? With covalent network, this is actually a large network. Kind of think lattice, but not necessarily. A large network of covalent bonds only. When I say network, sometimes you look at the particle diagrams and they're in the formation of like a crystal lattice, but it's not a crystal lattice like ionic. We don't have that positive, negative. Here you just see all these atoms are bonded, and those are the covalent bonds that are actually their intermolecular force. Melting points. We have low melting points for molecular, okay? And one thing to note is you'll generally see our molecular solids or liquid or gases at room temps. Their melting points are so low that you'll need to freeze them when we're at a room temperature situation. Ionic are going to have high melting points, but I want us to put high to very high, because this is going to come in to play here shortly. Metallic will have high melting points as well. Here, high to very high. Please note that these two, ionic and metallic, this is where some of those exceptions in our general trend may have overlap, okay? Covalent network are going to have super high melting points. Very high. So here, you know, if molecular has low melting points, I'm talking negative 10 degrees Celsius or even lower. And then you have a covalent network which has very high. If you're given Si and it has a melting point of like 2000 degrees Celsius, it cannot be a molecular solid. It has to be a covalent network, because I know Si is going to be our nonmetal. Conductivity. Molecular is not conductive or non-conductive. Ionic, as a solid, they're not conductive, but if it's a liquid or melted, yes, it is conductive. Metallic, it is conductive, and then covalent networks are actually not conductive as well. Any other characteristics to just kind of like put things together? They do have varied hardness. They're, again, weak IMFs, all covalent compounds with those weak IMFs. And when I say weak IMFs, I'm talking those LDFs, dipole-dipole forces, hydrogen bonding, okay? Ionic, they're going to be hard and brittle. And I'm sure you're sick of this equation. Coulomb's law is going to help us look at the strength, okay? Next, for metallic, they're going to be shiny. They're going to be malleable. They're going to be ductile. And they do have varied hardness. Here, based on, I'll put a star, based on size and valence electron. That's going to help us look at the strength of those metallics. For characteristics for covalent network, they are very hard, and that's because they have those very high melting points. Because they're interlinked with those covalent bonds, it does not have weak IMFs like the LDFs, dipole-dipole forces, and hydrogen bonding. Those are the biggest things that we have to get with the difference between the covalent network solid and the molecular. All right, so let's look at these particle diagrams, okay? So in this first example over here, you'll see in the first row, I kind of have particle diagrams not including charge. And then below, I show kind of like the charges to kind of help us understand stuff, okay? Some examples of molecular, you could say I2, CO2. And again, these are not the only examples. There's a lot of examples out there. So here, they're going to be held by weak intermolecular forces. These are nonpolar molecules. But yeah, you can see there's no charge on the bottom particle diagram. Next example, NaCl, magnesium oxide, great examples. You can see that plus and minus pattern, that lattice structure of our ionic compounds. Next, copper is a great example. You also can indicate alloys like zinc and copper. Here, I'm going to zoom in. You can see the electropositive elements, those positives, but don't think that they're actually charged like the cation, okay? Just because that negative left doesn't mean that it actually is charged in the sense. Those negatives, because they got delocalized, that's what caused that positive. But in a sense, they're just neutral, okay? I would never say this is copper 2 positive, okay? Next, let's look at the covalent network. I'm going to zoom in over here. So here, these are examples of carbon, all right? This right here is diamond, which is a 3D pattern of carbon. And the one on the right is considered graphite, which is considered a 2D arrangement of the carbon atoms. And you can see these lines in those structures, those are being held by covalent bonds rather than LDFs, dipole-dipole, and all that stuff. Another example, SiO2 is quartz. And again, you just have to look at the melting point. I know if I was just told SiO2, I would probably say molecular because Si and O are going to be nonmetals. But then if I'm giving a melting point that is super, super high, that tells me that has to be a covalent network solid because it wouldn't make sense for it to be in the thousands. And then based off this diagram, the gray that we see right here, that is our covalent bonding IMF, okay? All right. I have a you-do example for you, so why don't you pause the video and I want you to decide which one's going to be molecular, ionic, metallic, and covalent network based off the information given. There's no trick to this. You'll use every single one once. So let's talk about this example. I kind of actually highlighted the things that stood out to me that made me make the connection that this had to be that type of solid. So the metallic was the only one that had the high conductivity. Gonna be our metallic. So I knew that right off the bat. For the molecular, I noticed it had a low melting point. I noticed it had no conductivity, whether it was as the solid or if it was dissolved. Solubility in water just means if it dissolved in water, okay? The covalent network, that super high melting point, it was 1,670. That was a big indication of a covalent network, especially because it told me it was not conductive, okay? And then the ionic, it told me it was brittle. It told me that there was no conductivity unless it was melted. Those were the big indications of the ionic solid. All right. And last little thing to just talk about large molecules once again. We did talk about it in 3.1. I want to bring it back and talk about it again. So here, larger molecules will have the stronger intermolecular forces between them. And because, again, there's more areas of attractions, they're going to have those high melting and boiling points. So mentioned earlier, larger molecules we say are more polarizable because they have more electrons and more areas of attractions. I do want to note, like I was saying in 3.1, do not say mass or molar mass as the reasoning that, for the reason that this larger molecule has a higher melting point. You do not want to be saying that because, again, mass and molar mass is talking about the nucleus where our protons and neutrons are. That has nothing to do with intermolecular forces, those attractions. That's going to be coming from the electrons, aka it's more polarizable. It doesn't have more mass, okay? I mean, it does have more mass, but that's not the correlation between stronger intermolecular forces and higher melting point, okay?